Okay, so what do we do when the variance is not constant? We have to do a little bit more than complain. So there are two options. One is to find a new variance estimator that does not require a constant variance. That's the out-of-the-box solution. This topic is the robust standard errors, so this exists, and we have a whole slide deck on this later. This is a solution that is typically taught in economics. The solution that is typically taught in statistics is to transform the response to make the variance roughly constant. But the second option has a couple of disadvantages. So since it doesn't take much time, I will talk about the second option first now. But in general, this first option, in my opinion, is preferable. So, transforming the response. What do we do? Well, we transform the response using the log of y, or 1 divided over y, a square root of y, anything like that, so power transformations. Then we refit the model and check the diagnostic plot and see whether it's any better. And here are the examples that we have looked at. Here is, I guess, what I previously called another example. Non-constant variance here, log transformation, we get this plot. Do we now have roughly constant variance? Yes or no? I leave you to answer that question, and I'm moving on to the next example, and this is the auto data. For the auto data, we had this originally, and then I have two transformations here. And the question is, which transformation gets closest to constant variance, if any? So, all right. Do I have another example? No, that was the two examples. The disadvantages are twofold of this method. Number one, you have to do it manually, and everything changes every time. You know, you take a transformation and different variables are significant. And if you do any other things like model selection that comes later, then everything changes every time. So it's work. That's not the biggest problem. The bigger problem, in my opinion, is that it makes the interpretation not so interpretable. So for example, if we have the log of y, where y is the house price, and I have some x variables, and one of the x variables is the number of bathrooms. And then I want to say, what's the effect of, adding a bathroom on the house price? And I would say something with a log transformation, something like, adjusted for other variables in the model, blah, blah, blah. When adding a bathroom, the log price of the house increases by an average of beta $1. So what increases is not the price, but the log price increases. Now suppose beta is 2, beta 1 is 2, and I don't even know whether this is a good value, which is part of the problem. Now, if the log price increases by 2, what does that mean? Well, it means something, but it's not easily understandable, right? And since linear regression, in my opinion, is all about interpretation, this is not helpful. For prediction, there are very advanced prediction models that do a better job at predictions. Linear regression, for me, is explanation, understanding what's going on. And this is not helpful, in my opinion. All right. Do I have another slide? I think I do. Yes, some practical issues. As we all know, log 0 is not defined. But some of your data points may be 0. And so if your dependent variable has zeros, then you need to add a small value to all y's and then take the log. The definition of what is small depends on the range of the y values. If you have values between 100 and 1,000, then certainly adding 1 is good enough. If your values are all between 0 and 1, then maybe adding 0.1 is not a good choice. Then it may need a smaller value, certainly at least as small as the smallest value in your data set. So maybe a little smaller. Okay, so that brings us to the end of this diagnostics, and I'll see you in another round with another diagnostic.